This is AP Physics 1 2018 FRQ question. Transverse wave travels to the right along the string. So I know it is going to be transverse wave. And I know that transverse waves, if they have a point on the wave, even though the wave is traveling this way, every point on the transverse wave is traveling up and down perpendicular to the motion of the wave. Two dots have been painted on the string in the diagram below. Those dots are labeled P and Q. So I have a point P and I have a point Q. The figure below shows the string at an instant in time. At the instant shown, dot P has maximum displacement and dot Q has zero displacement from equilibrium, and the dotted line is your equilibrium. At each of the dots P and Q, draw an arrow indicating the direction in the instantaneous velocity, the direction of the instantaneous velocity of that dot. If either dot has zero velocity, state V is equal to 0 next to the dot. So point P reached its maximum displacement. At this moment it stops. It's like if I throw a ball forward or upward, it will reach its maximum velocity and stop for like fraction of a second and then starts falling down. So the same happens to the point P. It reached its maximum velocity. It was moving in this direction. It reached its maximum velocity. It has to stop before it switches its direction in the opposite direction, because it will be traveling perpendicular to the motion of the wave. So the velocity at point P is equal to 0, and velocity at point Q, as the wave is moving forward, the Q is gonna appear right here. As the wave is moving forward, the Q is gonna appear right there. So the Q is gonna be traveling from point to point to point, but it's all gonna be staying. The matter in the wave does not move. The energy is moving. So the point, every single point on the string pushes the following point either up or down. So the Q is gonna stay in this line. It's just gonna go up and down. The string itself is not moving. The wave is moving. So from this picture, I see that because this one is higher than Q and the wave is moving this way, I know my Q is going to move in this direction. So that's going to be the direction of the Q at that point, at that instant. For the second part, they say on the figure below, show this string at the same instant as shown in part A. So it's the same time as the previous one. At each of the dots P and Q, draw an arrow indicating the direction of instantaneous acceleration. So now I have to find the direction of the acceleration of that dot. If either dot has zero acceleration, state acceleration is equal to 0. So at point P, point P does not want to be where it is. It's displaced from its equilibrium. So it will accelerate toward the equilibrium. If the point P was on the top, it would accelerate toward the equilibrium. But point Q is already at the equilibrium. So point Q has acceleration equals to 0. It doesn't want to be misplaced from the point where it is. But point P is going to be accelerating toward the equilibrium. So that would be your directions for acceleration in A. For the B part, the figure below represents the standing at the time t equals 0, the same instant as shown in part A, when the P dot is at its maximum displacement, and again we see the P dot right here, from the equilibrium. For simplicity, the Q dot is not shown. So for the B part 1, on the grid below, draw this string at the later time t equals to 1/4 of the period. So let me look at the period first. So the period would be this much. This much. This is the period. And 1/4 time less. So I have, every wave has 4 parts. 1, 2, 3, 4. So one full wavelength or one period will have 4 parts. So if I want to see my graph t over 4 time later, then that would look like this. They ask me, draw the string at the later time t t over 4 time. Note, do not do any scratch practice work on the grid at the bottom of the page. Only the sketch made on the grid immediately below will be graded. So the only grade wherever you place on the grid. So you could do this work right here, but they will not count it. So that means your solution must look like this. So that would be your solution. And because of the way the wave is continuous, I just shifted the whole wave this way. It's for you to see how it shifts, 1/4 position. But because the wave is continuous, so I still have to continue this part as well. For the next part, on your drawing above, draw a dot to indicate the point of dot P on the string at the time t equals 1/4. So if I look where my t was located, my p was located, my p is located right here, right? So the p only can move up and down. The p does not travel with the wave. The p only travels within its position where it is located. The wave is traveling this way, but p, the matter, every single point, every single molecule in the wave will move perpendicular in a transverse wave to the motion of the wave. So I know that that happened at 6, 12, 18 seconds, 24 seconds. Oh, centimeters, sorry, it's centimeters. So I have to go to the same position, 18, and place my dot. So my dot P is right here. And then for C part, now consider, let me shift a little bit so consider the wave at time t equals t for the full period passed. Determine the distance traveled, not the displacement, by the dot P between t equals 0 and t equals t. So let's look at this part back right here. So the dot within the period will travel from here all the way till here and back to original position. So that means that's the period, right? So from this point back to this point is one period, or the full wavelength. So that means this dot P must travel all the way to the top and to the bottom. What distance does it travel? It travels this distance and back this distance. So it travels twice this distance. That's going to be distance, that's not displacement. Let's see what they're asking us. Are they asking us for displacement or for the distance? Determine the distance traveled, not the displacement, by the dot P between the times t and t. T equals 0 and t. So looks like this distance here is 16 centimeters, but it's twice this much. So that means 32 centimeters. So the wave is going to travel 32 centimeters. And I think they give you the space right here at the bottom for your work. And that's about it for this question. 2018 AP Physics 1 FRQ. Also, before you leave, always follow the links below the videos that I post, because I post the videos, the questions themselves. So before every question, before you watch my video, try to solve the question yourself first, because one thing is to watch, the other thing is to try to do it yourself. When you do it yourself, you make mistakes. When you make mistakes, you learn better than if just watching somebody. I always tell my students that watching a sport that you like watching, baseball, basketball, football, whichever you watch, you always criticize the players, but you yourself cannot go and play that game. You need to do a lot of practice, physical exercising, in order to be able to play good. And just watching somebody does not help you to learn. So always spend time on practicing, doing the problems, and then if you're stuck somewhere, seek for help through the videos that you're watching.